Hello, this is Mrs. Nearing, and we'll be talking through problems number 3 and 4 on the Kinetics practice set number 3. There's a different video covering the first two problems from this practice set. So problem 3, it's an AP release problem, and again, some of these are trickier than our kind of standard simple ones that we started out with. So if you look here at this, we've got our overall reaction right here, and we are trying to figure out what the rate law is, and we're given some data comparing molarity and the initial reaction rate. So what we want to do is isolate two experiments where we're changing only one variable at a time. So if you look at comparing experiments 1 versus 2, what happens in experiments 1 versus 2 is the concentration of ClO2 stays the same, but the concentration of F2 goes up by 4. Okay, so it goes from 0.1 to 0.4. And if you look at what happens to the rate, 9.6 divided by 2.4, they're both times 10 to the third. The rate goes up by 4 as well. So, and remember, our goal here is we're trying to figure out, rate equals K times ClO2 to some exponent times F2 to some exponent. And, in order for this to make sense, you're trying to figure out what the exponent is around the F2. If the exponent is a 0, then any number to the 0th power is 1. So if it were 0 order F2, then we would expect the rate to not change. If it were first order, then 4 to the power of 1 is equal to 4. If it were second order, then 4 squared is 16. You expect the rate to go up by 16. So the scenario that matches our data is that F2 must be first order, because when you quadruple the concentration of F2, the rate also quadruples. So let's go down here to this and fill in that we know for F2 is first order. Okay. Now we got to figure out, what about the other reactant, ClO2? Well, unfortunately, when we're looking at ClO2, there are no two reactions in which the F2 concentration stays the same. But we're going to do what we did earlier in problem number 2, and we're going to think about what our possibilities are. So we know for sure, let's think about what we know for sure so far. We know that F2 is first order, and we know that ClO2 is either 0, first, or second order. So to write down our options, ClO2 could be 0th order, in which case the math would look like this. It could be first order, or it could be second order. I ran out of room, so I'm going to do this over here. So let's pick the two experiments in which our concentration of ClO2 is changing. So let's compare experiments 2 and 3. And if we look at experiments 2 and 3, what happens is the concentration of ClO2 doubles. So I'm going to write here 2. This is doubling. And what happens with the F2, you have to be careful here, the concentration of F2 is actually being cut in half. So scenario 1, if ClO2 is 0th order and F2 is first order, this would be 1 times 1/2. So I'd expect the rate to be cut in half if this were 0 order. Let's think about this scenario. What if ClO2 were first order? Then this would be 2 to the power of 1 times 1/2 to the power of 1. So this would be 2 times 1/2. So in this scenario, the rate would remain unchanged. And over here in this scenario, when I double ClO2 and F2 is cut in half, whoops, I just realized I made a mistake here. This is actually supposed to be a 1. Okay, so we've established we already know F2 is first order. So in this scenario, it would be 2 squared, so 4 times 1/2. So in this scenario, the rate would double. And what happens when we look at the rate, it goes from 9.67 to the negative third to 9.67 to the negative third. So the rate stays the same. So the scenario which fits is, it looks like this one right here. So this would only make sense if ClO2 and F2 were both first order, because when you double this and cut this in half, you'd end up with the rate staying the same. So let's go down here to our rate law and fill in that the reaction order for Cl2 is also 1. So this right here is our rate law for this reaction. They're both first order. Okay, so now let's go down and see which of these reaction mechanisms would fit with this rate law that we just determined. So if we scroll down here, so they give us two possibilities. We want to work through the possibilities. So if 1 was our reaction mechanism, we're going to look here at the slow step. That's our rate determining step. And there's only one molecule involved in that rate determining step. It is ClO2F2. But if we look up here at our reaction, it looks like ClO2F2 is not a reactant. My reactants are ClO2 and F2. So ClO2F2 looks like an intermediate, and I can't have an intermediate in my rate law. So when I have an intermediate involved in the slow step, I go back and I say, well, how was this intermediate made? And I'm going to substitute in these two molecules right here. So wherever I see ClO2F2, I'm going to substitute in ClO and F2. Okay, so my rate law ends up being rate equals K, and instead of writing in the intermediate, I'm going to write in ClO2 and F2, because the intermediate was made by adding together one molecule of ClO2 and one molecule of F2. So this is my rate law for this reaction mechanism. If the second was my reaction mechanism, I'd say, okay, my first step here is the slow step, and the slow step involves one molecule of F2. So the rate law for this scenario would be rate times K, so rate equals K times F2. Which of these fits this rate law that I just wrote? It looks like this mechanism is the one that fits, because we determined in part A that ClO2 is first order and F2 is first order. So that means this is the correct mechanism. All right, let's take a look at this last problem here, number 4. Similar kind of setup here. We've got some molarity versus rate information. You want to determine the reaction order from the data, show your reasoning. So when we're determining the reaction order for H2, we want to compare experiments 1 and 2, because in experiments 1 and 2, the concentration of NO remains the same. So NO remains the same. The H2 concentration doubles, and if we look at what happens to the rate goes from 1.8 to 3.6, so the rate also doubles. So therefore it is looking like H2 is first order, okay, because 2 to the power of 1 is, so we're saying this exponent here must be a 1. Okay, so let's look at NO. We want to compare two experiments where the hydrogen concentration stays the same. So if we compare experiments 3 versus 4, when your the NO concentration doubles and H is staying the same, it looks like the rate goes from 0.3 to 1.2. So the rate quadruples. So when NO doubles, the rate quadruples, therefore this exponent must be a 2. So NO must be NO must be second order. So the overall rate law is rate equals the rate constant K times H2 being first order, and NO is second order. So it's H2 times NO squared. And the 1 you could write in if you want, or leave it off. So if you don't write anything, then that means a 1 is assumed. So then we want to calculate the value of the rate constant K. So what we do here is we're just plugging numbers into the rate law that we just wrote. So you can choose any of the experiments. I'm going to choose experiment number 1. So my rate is 1.8 times 10 to the negative 4th. The units here are molarity per minute. Okay, make sure you read this data table carefully. Most of the time they're in molarity per second, but sometimes they might be in molarity per hour or molarity per minute. So make sure you look at your data table carefully. And then K, we don't know. H2 is 0.0010 molarity, and then NO2 is 0.0060 molarity squared. Let me draw a line there to simplify that out. Okay, so in order to solve for K, we're going to have to divide both sides by 0.0010 molarity times 0.0060 molarity squared. And then let me erase this over here. So when we solve for K, numerically, when we divide this, we end up with the number 5.0 times 10 to the negative third. This has 2 sig figs in it, like all of our other numbers did. And then if you look at your units, one of your molarities cancels out, and you're left with 1 divided by minutes divided by molarity squared. So you could write that as 1 over minutes molarity squared. You could also write that as minutes minus 1 molarity to the minus 2. Sorry, that's written kind of awkwardly because I ran out of space. But this is your units as 1 over minutes molarity squared. Okay, so pay attention to units when you're calculating your K values there. And this is a little bit different scenario. They give you a proposed sequence of steps. You need to figure out which is the slow step. And so if you think through your options here, let's think through it. If 1 were the slow step, then the only thing involved in the slow step are 2 molecules of NO. So if 1 were the slow step, then rate would be equal to K NO squared. Okay, that doesn't match the rate law that we just figured out up here, so it must not be 1. What if 2 were the slow step? So if 2 were the slow step, then the rate would be equal to K, and I got 1 molecule of N2O2 and 1 molecule of H2. Remember that N2O2 is actually an intermediate. Okay, so wherever you see N2O2, we're going to substitute in NO and NO. So we're going to substitute in NO squared wherever you see N2O2. And now this actually matches our rate law. It's second order for NO and first order for H2. So that means that our second step must be the slow step, because that would work out and actually match our rate law. So it asks us to show that this slow step would match with the observed rate law, which is kind of what we're doing here. You want to also show that it matches the overall stoichiometry. What that means is you want to show that when you add together these reaction steps, you end up with an overall reaction that matches the one that is given up here. So notice up here at the beginning they told you this is the overall reaction. So you want to check this mechanism and say, okay, when I add up these three, okay, it's hard to scroll down here. When I add up these 3 steps, which are kind of, it's hard to read now, so let me erase my writing. When you add up these 3 steps, does it match the overall mechanism? Okay, so it looks like, let's check this. We've got an intermediate that cancels out here. We've got another one here. What we're left with is 2 NOs on the left, and then I've got 2 H2s. And on the right, I've got 2 waters, and I've got 1 N2. And you want to compare this, again, go back up to the top of the page and compare it to right here, and it seems like that is a match. So our mechanism matches the overall stoichiometry of the reaction, as well as it fits our rate law in terms of if the second step is the slow step, remember that's what I erased earlier, then we end up with a rate law that matches what we just figured out up here. Okay, so that's the end of this practice set.